Okay. So, welcome to today's session. Today, we are going to discuss some numericals based on the problem, based on the theory, what we have discussed in last lecture. So, just I am going to remind the last part of the last lecture, that is the summary of the losses, what we have studied up last lecture. So, in last lecture, we have discussed that uh, the different types of losses we have discussed in up to last lecture. Okay, in that we have discussed that the mainly the type of losses like elastic shortening of concrete, that whatever loss is happening due to the elastic shortening of concrete, due to that some effect on the prestressing force what we have applied is going to take place, and that can be calculated by using the equation m into fc, where m is the modular ratio which can be calculated by using relation epsilon es, that is modulus of elasticity of steel, to the modulus of elasticity of concrete, that es by ec. By using this we'll be able to find out the modular ratio m. Now again, by using the next concept, that is shrinkage of concrete, that as we know that the concrete is having properties in fresh state and as well as in hardened state. So shrinkage is the one of the property of concrete when that concrete is in fresh state, that, or we can say that when that concrete is going to change from fresh, that is from liquid to solid phase, that whenever that concrete is in plastic phase, at that time this shrinkage occurs, and mainly this occurs due to the reduction of water available in that concrete. Okay, so that shrinkage losses we have evaluated. That shrinkage losses can be calculated by using this relation epsilon cs, which is the strain due to shrinkage in concrete, and es is the modulus of elasticity of steel. So by using this relation, we'll be able to calculate the shrinkage losses. Then the third loss what we have discussed is the loss due to the creep of concrete. Again, we know that creep of concrete is a property of concrete which is a long lasting property or long going property, in which the concrete is going to deform continuously throughout its life due to the application of forces, whatever forces to which that concrete member is subjected. Due to those forces, there may be very minor deformations in that concrete, but we have to consider these deformations or this change in the concrete so that we can assess the amount of losses which are happening into the steel. So these creep losses can be evaluated by knowing the creep coefficient. That creep coefficient is phi. This creep coefficient is nothing but it is the ratio of elastic creep strength to the elastic strain. But if we know that the value of creep strain, and if we know the elastic strain, then by using that relation we'll be able to find out this value phi, creep coefficient, and m already we have discussed es upon ec, and fc is the stress in the concrete at the level of steel. So by using this we'll be able to find out the loss of prestress in case of creep of concrete, or you may use this relation, that is fc into epsilon c into es, where fc is stress in concrete at the level of steel, ec is the creep strain which is going to develop. That creep strain is nothing but by it is the amount by which the concrete is going to shorten, or that whatever change in length is happening in that concrete. Okay, so this is about creep of concrete. Now next is the anchorage slip. Anchorage slip, it occurs due to the slip of anchorage system what we have adopted. So here we are using again one relation delta. Delta is the slip of anchorage, means by how much distance that slip occurs. Slip occurs means that whatever anchorage that we are using, it is going to shift its original distance by a certain amount. It may be due to any defects or any other reason also. So delta is that slip or the distance by which that slip of anchor system occurs. E is modulus of elasticity and L is the length of the member. Okay, so these are the main losses: elastic shortening, shrinkage of concrete, creep of concrete, and anchorage slip. These are the four losses what we have discussed. Along with this, again one more loss, two more losses are there. Total 6 losses we have to consider. So the next loss is the loss of stress due to relaxation of steel, and last one is the loss. Last loss is the loss due to the length effect and the curvature effect. So that we'll discuss after discussing these problems. So now we are going to discuss one simple numerical based on this all four losses. So let us go to that. So just in this numerical that they have given that there is a prestressed concrete pile which is having a size of 300 mm by 300 mm in section and is provided with 40 wires. It provided with 40 wires. The size is 300 by 300 mm and the wire is of 3 mm diameter. Each wire is having 3 mm diameter, distributed uniformly over the section. So this line is very important. Distributed uniformly means all these 40 wires are distributed uniformly all over the section. Initially, the wires are tension in the prestressing bed with a total pull of 450 kilonewton. Initial prestressing force is given. Determine the final stress in concrete and the percentage loss of stress in the wire. So we have to find out the final stress, means initially we have to find out the loss of prestress, so that the loss of prestress will gives us that the final stress, that is total initial stress minus loss of stress will get the final stress. So for that what they have given, that we have to take the value of ESC, that is ES, it is ES, that is modulus of elasticity for steel, that is equals to 2.08 into 10 raised to 5 Newton per mm square. Modulus of elasticity for concrete EC is equals to 3.2 into 10 raised to 4 Newton per mm square. Creep shortening. Creep shortening is given equals to 32 into 10 raised to minus 6 mm per Newton per mm square for stress. So it means that they have given the value of epsilon C directly. So they have given the value of epsilon C, means it is the creep strain. Okay. Then the total shrinkage strain. Total shrinkage strain they have given 200 into 10 raised to minus 6. So total shrinkage strain means they have given the value of epsilon CS. Epsilon CS is equals to 200 into 10 raised to minus 6. Shrinkage strain they have given. Then the relaxation loss. Relaxation loss in steel is 4.5% of the initial stress. So just as I told you that relaxation loss we are going to discuss after some time. But while discussing this, I'll explain that what is the meaning of relaxation loss. So these are the losses what we have to consider, and by considering all this, we have to find out the total loss of stress. Okay. So let us solve this problem. So as I told you initially, that in this problem they have provided us the values just like they have given the section size. Section size, that the section is having a 300 mm by 300 mm pile. So this is the pile which is having a size of 300 by 300 mm. Both length, width and depth is same. Square pile is there, and this pile is provided with 40 wires of 3 mm diameter. 40 wires means they have, and again one more point is that all these wires are uniformly distributed. Uniformly distributed means they have divided this wire or distributed this wire all over this section uniformly, all over the section uniformly like this. Okay, so these wires may be provided over the entire section. Entire section they have provided the wires like this. Okay, so it means that These wires are going to produce the total compression over all over the section. So we can say that there is no eccentricity of prestressing force. That is, total prestressing force is going to act all over the section. So that eccentricity is not going to happen there. And they have given that initially the wires are tension in the prestressing beds with a total pull of 450 kilonewton. So total pull means they have given the value of P. So we can take that P naught as the initial prestressing force. So P naught is 450 kilonewton. Okay. So these are the values they have given. So now we have to find out the total final loss. Okay, so for that, let us go to the next point. That is, as I told you, that the initial force they have given, initial prestressing force P naught is given 450 kilonewton. Now we have to calculate the area of wire. Area of wire they have given that 40 wires are there. So out of these 40 wires, the 40 wires are there. So we have to calculate the area of wire. So that area of wire comes to 282.74 mm square. The initial stress in concrete we have to calculate by using these two values, that is the P naught and the area of concrete. So that will be equals to Fc will be equals to P naught upon A. So it comes to 5 Newton per mm square. That is the initial pre-stress in the initial stress in concrete, not pre-stress. Initial stress in concrete is 5 Newton per mm square. Okay. Now the initial stress in wires we have to calculate. So again, for that what we have to do, that we have to divide this total pre-stressing force with the cross-sectional area, so that we will be able to calculate the stress in wires. So area of total pre-stressing force 450 into 10 raised to 3, that is 450 kilonewton, divided by area of all wires. So that you will get the total pre-stress or initial stress in the wires, which is 1591.57 Newton per mm square. Okay. Now, because these all values we have to use in order to find out the losses. And the modular ratio M is equals to ES upon EC. So ES value they have given 2 into 2.08 into 10 raised to 5 and 3.20 into 10 raised to 4. So that is equals to 6.5. Now simply what we have to do, that we have to put all these values in the equations what we have derived for the losses. Okay. So the various losses are as follows. That the losses are that loss due to elastic shortening of concrete. The first loss, that we can calculate the loss due to elastic shortening of concrete by using relation M into Fc. The value of M already we have calculated, M is 6.5, Fc is 5. So just multiply these two values, so that we'll get the loss due to elastic shortening as 32.5 Newton per mm square. Then loss due to creep of concrete. So as I told you, this value we can calculate by using two methods, either by using creep coefficient method or by using the other relation, because the creep coefficient value needs that creep coefficient value is nothing but it is the ratio of pi is the ratio of creep strain to the elastic strain, epsilon e. But the epsilon e value is not given, but the value of creep strain is given in this problem. So that we'll be able to use the other relation, that is epsilon c into fc into es. Okay, so by using this relation, we'll be able to find out the loss due to creep of concrete. So by using same relation, here it is given. So loss due to creep of concrete is equals to, just put this value, epsilon c is given 32 into 10 raised to minus 6, fc already we have calculated 5, es is also given. So that loss due to creep of concrete is 33.28 Newton per mm square. Now loss due to shrinkage. So for this we have given the shrinkage strain. So shrinkage strain value epsilon c is they have given, and shrinkage strain into modulus of elasticity for steel. This product will gives you the final loss. So as per the IS 1343 recommendation, we have to find out the shrinkage loss by considering this product of epsilon CS into ES. So this is the loss due to shrinkage 41.60. Now one more loss they have given, that the 4.5, that is relaxation loss. Relaxation loss is the loss which is normally provided, normally occurs that when we are pulling the tendons, we are going to apply, or we are supposed to apply a prestressing force, desired prestressing force. So as in this problem, they have given that the desired prestressing force is 450 kilonewton. But what happens that when we release that tendon, so just when we remove the hydraulic jack, then what happens? Some of that prestressing force is lost due to the relaxation of that cable. Means initially we are stretching that wire, and then we are going to release those wires. So due to this releasing process, this some amount of stress is going to loss, and that loss is called as the relaxation loss. Okay, or maybe due to the atmospheric conditions also, that due to the change in temperature also, sometimes what happens that as the temperature increases, we know that the steel is having a tendency to expand, and as temperature falls down, it's going to short. So due to this process also, there may be possibilities of relaxation of stresses, or the amount of stress present in that wire, it may be changes. So that relaxation loss is given in IS 1343 values. Different values have been given there. We'll discuss afterward. So that value here they have provided. So that 4.5% of relaxation losses they have given. So that the 4.5% of the initial stress in wire is going to loss. So that's why 4.5% means 4.5 divided by 100 into initial stress in wire. Already we have calculated. So that comes to 71.62 Newton per mm square. That is the loss of stress due to relaxation. Okay. So now to find out the total stress, we have to take addition of all stresses what we have calculated. That the loss due to elastic shortening, loss due to creep of concrete, loss due to shrinkage of concrete. So here's all these values we have to find out, or we have to add, get the final loss. Okay, so that addition comes to 179 Newton per mm square. Now the effective pre-stress available in wire we have to calculate. So that initial minus this loss will get the effective pre-stress available. Okay, so that comes to 1412.57 Newton per mm square. Now we have to calculate the percentage loss. So initial, the percentage loss we have to calculate. So for that, the loss of pre-stress divided by the initial pre-stress into 100, you will get the percentage loss. So here it comes to 11.25%. Okay. So now again, in reverse direction, you have to calculate the final stress available in the concrete. FC value, revised value of FC we have to find out after loss. So the total effective stress in wire is 1412.57 Newton per mm square into you have to find out the you have to multiply it with the area of wires. So that area of wire we have calculated 282.74 and divided by cross section of the concrete, that is B into D of concrete. So you will get the final stress in concrete as 4.44 Newton per mm square. Okay. So this is the total final stress in the concrete after all losses. Okay, so this is the revised value of stress, FC, final stress in the concrete after losses. Initial stress we have calculated here. This value of FC we have calculated here. Initial stress in concrete, FC is equals to P naught upon A, where P naught is the initial stress. Just what we have to find out, that the final stress we have to calculate, and that final stress comes to the area of wires into the stress in the wires. Okay, so that we have calculated here, the stress in the wire into area of wire divided by area of concrete. So this is the end of our final answer of first problem. We'll discuss second problem. So let us go to the next problem now. Numerical number 4. So in this problem, there is a pre-stress or pre-tension concrete beam. Remember this word carefully. Pre-tension beam of 250 by 360 mm is prestressed by 10 wires of 8 mm diameter. Initially, stress to 1000 Newton per mm square. The center of the steel wire is located at 105 mm from the soffit, means from the bottom. Determine determine the maximum stress in concrete immediately after transfer, allowing elastic shortening of concrete only at the level of the center of steel. Okay? Sorry. Only at the level of steel. So elastic shortening is there. Elastic shortening is happening. So it means that we have to calculate the loss due to the elastic shortening of concrete also. Okay, at the level of center of the steel. If, however, the concrete is subjected to additional shortening due to creep and shrinkage, and the steel is subjected to a relaxation of stress of 5%, find the final percentage loss of stress in the steel wires. For that, take ES equals to 210 kilonewton per mm square, EC equals to 36.85 kilonewton per mm square. Creep coefficient phi, this value of creep coefficient they have given now. Creep coefficient phi is 1.6 or 1.60, and total residual shrinkage strain is equals to 3 into 10 raised to minus 4. Okay, so these values are given here now. So the given values are just like this, that the value of ES is given to 210 kilonewton per mm square, EC is given 36.85 kilonewton per mm square, creep coefficient phi is given 1.60, total residual shrinkage strength that they have given means that they have given the epsilon CS, this value they have given, and in this they have given the section size 250 by 360 mm. 10 wires are there of 8 mm diameter, so that we'll be able to calculate the total area of wires, and each wire is stressed to 1000 Newton per mm square, so that we'll be able to find out the total prestressing force P naught also, initial prestressing force. And they have given that these wires are located at 100, centered of these wires is located at 105 mm from the soffit. So means here we have to find out the eccentricity also. Okay. So this is the condition now, that this they have given the beam which is having a section properties or section size 250 by 360. 250 is the width and 360 is the depth. So they have given that the tendons, center of tendon is located at 105 from the bottom. So this distance they are given 105, and now we have to find out the eccentricity E. So that eccentricity E will be equals to 360 divided by 2, that is 180. 360 divided by 2 means this distance is 180. 180 minus 105. So that's why 75 mm will be the eccentricity. Okay. So that eccentricity we have calculated. So now remaining values we have to find out, that losses lost due to the elastic shortening of concrete, as told here, that additional shortening due to creep is also going to take place. So we have to calculate loss due to creep of concrete. Again, shrinkage is also happening. Loss due to shrinkage is also need to be find out. Loss due to shrinkage, and steel is subjected to a relaxation. So relaxation loss is to be also determined. So total how many losses we have to calculate here? That we have to calculate the loss due to the elastic shortening of concrete, then loss due to the creep of concrete, then loss due to the shrinkage of concrete, loss due to the relaxation of concrete. So all four losses what we have discussed, we need to find out all those losses. Okay. Now let us see that the solution of this problem. So area of beam 250 into 360, 900, 9 into 10 raised to 4 mm square is the area. Moment of inertia is need to be calculated here because we have to find out the stress in concrete at the level of steel as mentioned in the problem itself, that we have to find out the concrete only at the level that the elastic shortening of concrete only at the level of centroid of steel as they have mentioned here. So we have to find out the stress in concrete at the level of steel. So for that we have to use relation Fc is equals to P by A into P square by I. So for that we have to find out the I. So I is BD cube by 12, 9.72 into 10 raised to 8 mm4. Eccentricity, as I told you, it is 180 minus 105, so 75 mm is the eccentricity. Modular ratio ES by EC 5.70. Area of wires, that in that problem they have mentioned that there are 10 wires of 8 mm diameter each, so we'll be able to find out the area, number of wires into area of one wire. 502.65 mm square is the area. Now as they have mentioned that the stress in wire as 1000 Newton per mm square. So we have to find out the initial pre-stressing force P naught just by multiplying 1000 with this value 502.65. So that's why P naught is the initial pre-stressing force. P naught is equals to area of that's initial stress in wire into area of wire. So you'll get the total pre-stressing force 502.65 kilonewton. Okay. Now we have to find out the stress in concrete at the level of steel. Means at the level of steel, steel means what? That we have provided a beam along with a tendon. So this tendon is located at this distance somewhere that is 105 mm from the bottom. So we have to find out the stress in concrete at the level of steel. Means where the steel wires have been provided at the same level, what will be the amount of stress in concrete, that we have to find out. Okay, so for that we are normally using this relation Fc is equals to P naught upon A plus P naught into E square by I. Now how this is calculated? So just simply this is the direct stress due to the tendons, and this is the bending stress due to the tendons what we have provided. Okay, so that value of Fc comes to 8.5 Newton per mm square. What we did here, that we have simply put the values. P naught already here we have calculated 502.65 kilonewton. Area of concrete section already here we have calculated. So, and eccentricity is also calculated here. Value of moment of inertia is also calculated. So put all these values in this equation so that we'll be able to find out the value of Fc. Okay, so this Fc comes to 8.5 Newton per mm square. Fc is the stress in concrete at the level of steel. Okay, now we have to find out the losses now. Okay, so the losses, different types of losses we have to calculate. So first, initially we'll go to the loss due to shortening, elastic shortening of concrete. So that elastic shortening of concrete loss can be calculated by using relation M into Fc. Okay, the value of Fc already we have calculated here, 8.5, and the value of M is already calculated here. So just simply by multiplying these two values, we'll get the loss due to elastic shortening of concrete. So loss due to shortening of concrete will be equals to M into Fc. So put these values. 5.70 is the modular ratio. Fc will we have calculated. So the loss due to elastic shortening comes to 48.45 Newton per mm square. So let us consider this as 1. Okay, first loss. Then we have to calculate loss due to the uh, second loss, that is loss due to the shortening. Okay, so now we are going to calculate the stress in wires, that because what is the condition that in that problem, as I told you, remember this point, in this wire, in this problem they have mentioned that pre-tension beam. Pretension beam is there. Pretension beam, in this pretension beam, we are applying the tension to the wires, and then we are providing the, we are doing the casting. Okay, so that elastic shortening is occurs at different levels. So we have to calculate the all losses. So that we have to deduct this loss in the prestress, that this amount of loss of prestress from the initial prestress. Okay, so initial prestress in wires is 1000. So 1000 minus 48, you will get the now the available stress in the wire. So that available stress in wire is 951.55 Newton per mm square. Okay, so this is the stress in wire after loss due to elastic shortening of concrete. Now, that what is the available prestressing force now, that we have to calculate. So that available prestressing force P is equals to that available stress in wire into area of wires. Available stress in wire is 951.55, and area of wire already we have calculated. That area of wires here we have calculated 502.65. So that area of wires multiplied by available stress in wire, you will get the total prestressing force available after elastic shortening of concrete. So this is the prestressing force available after elastic shortening. Now again we have to calculate the actual stress in concrete at the level of steel after this first loss. So simply again put this values here, the value of P, revised value of P, this value, and eccentricity and moment of inertia and area is remain same because concrete section is going to remain same. Okay, so put this value and other values also, so that we'll get the stress in concrete after elastic shortening, and that is after elastic shortening, that this much amount of stress is available in that concrete section after loss of stress due to elastic shortening. Okay, so this is the revised value of FC. Now we have to use this revised value of FC to find out the other losses. The other losses are that loss due to the elastic shortening, already we have calculated 48.5. Then the loss due to creep of concrete. So this creep of concrete, for that creep coefficient they have given in the problem. Creep coefficient of that value of phi is given 1.6. Value of phi is given in this problem statement itself here. That creep coefficient phi is equals to 1.6. So we have to use this value directly. So put this value phi, m already we have calculated 5.7, and fc, the revised value of fc we have calculated here. So put this value so that we'll get the loss of prestress due to creep of concrete. Okay, so this is the loss of prestress due to creep of concrete. Now the loss due to shrinkage of concrete. Now remember that shrinkage, creep, these are the properties of concrete which are going to take place simultaneously. So that's why we have to consider the same loss or same stress in concrete here also. So again, that loss of loss of stress due to shrinkage of concrete. So for this, in this problem, they have given the value of shrinkage strain, epsilon CS they have given. So that value of shrinkage strain given equals to 3.3 into 10 raised to minus 4. Okay, so simply put this value. ES already have given 210 into 10 raised to 3 Newton per mm. That value of ES Newton 210 kilonewton per mm square they have given. So simply the loss due to the shrinkage of concrete comes to 63 Newton per mm square. Okay, and the last loss what they have asked to find out is the relaxation loss. Relaxation loss. So 5% relaxation is allowed there. So 5% of the initial prestress is going to reduce. So now remember here we have to consider the initial prestress while calculating the loss due to relaxation, because what is happening, as I told you, that relaxation loss is occurred due to the removal of jacks, or it occurs during the transfer phase only. Transfer phase means that when we are applying the pull, to the tendons by using any method, by using hydraulic jack or any other method, we are going to, it is supposed to apply the desired force or desired stress in that wire, tension in that wire. So that initially this tension is, means the desired amount is 1000 Newton per mm square. That much amount of stress is to be applied. But what happens that during that release of wire or during the total entire lifetime, that 5% of it, this loss may get, that 5% of this stress may get lost as a relaxation loss. So that's why we have to reduce this amount from the initial stress only. Okay, so that's why 5% is reduced from initial stress. Initial stress is 1000, which is given. So just deduct this value from this so that we'll get the available stress. So available stress, that loss of stress due to relaxation is 50 Newton per mm square. Okay. So now what we have to do, that we have to find out the total loss. Total loss is nothing but addition of this value, first, second. So this is the first, again we have written here. This is the second loss. Then this is the third loss due to shrinkage, and this is the fourth loss due to the relaxation. So just simply add equation number 1, 2, 3, and 4. You will get the final loss. So that is equals to 235.14 Newton per mm square. Okay. So now I have to calculate the final percentage loss of this uh, total loss. So that comes to this total loss divided by initial loss into 100. You will get the percentage loss. So here the 23.51% of stress is going to loss. So this is a considerable amount. That whenever you are going to apply a pre-stress of 1000 Newton per mm square to the wires, out of this 1000 Newton per mm square, 235.14 Newton per mm square stress is going to loss due to various reasons. That is due to the relaxation of wires, due to the shrinkage of concrete, due to the creep of concrete, and due to the elastic shortening of the concrete. This much amount of stress is going to reduce. Okay, so that's why we are saying that it is very important to find out these losses. Okay, because suppose now if we neglect this kind of losses, that if suppose we neglect this amount of loss, and if we provide the concrete member as it is, then what happens that where what the actions are assumed, that the concrete section is going to take this much load and this much bending moment even after applying this much stress, that all assumptions will fail. Okay, because we have calculated all the stresses, all the bending moments and other values, the reinforcements based on the not stress that you have provided. But actually in practice, due to the losses, that available pre-stress is less as compared to the design stress. Okay, so that's why this amount of losses is need to be calculated, and that much amount of stress is to be applied additionally when we are going to apply the pre-stress in the cables. Okay, so now suppose here the 23.51% is loss. It means that you have to apply an additional value of 23.51% of 1000. Okay, so it means that you have to apply the total load of 1235.14 Newton per mm square to the wire, so that after losses you'll get the 1000 Newton per mm square stress in that cable or in the total section. Okay, that is the requirement why we are calculating the losses. Okay, so if you have some queries, you may directly ask to me, you may post it in chat or in the comments.